Thank you, Dr. Grant, and good morning to everyone. I want to thank you for the opportunity to come and tell you about some of the things that we've been doing this year. I also would like to thank Catherine Nix and Dave Paulson for all the meticulous work they did in conducting the test on which I will report today. And I'd like to begin by saying that my basic desire and my goal and focus is to control WTB using biological control efforts, especially the predators and parasitoids that might be located in our forest here in East Tennessee. So that's what most of our energy is directed against. But in order to do so, you must have a sound fundamental understanding of the insect's biology. And while aspects of its development and its behavior are known, many fundamental and basic aspects of its development remains unknown. And so I'll give you some overview of that today. And I'll start off with one of the first tests that we did, and just say that one of the things that you have to do first is to identify the problem, identify the pest. And in order to have a confident identification, because there's other bark beetles that also hit walnut, as other trees, it would become confusing and almost a hodgepodge of efforts involved to come up with the correct ID. In order to do that, what we did is that we began to look at some of the morphological features using scanning electron micrographs to evaluate features that exist on a known WTB specimen or specimens. And so we were hoping that we could find something that would give us more confidence in saying, yeah, we're working on WTB and not just some ambrosia beetle that we misidentified. If we take a look at WTB, let me see if I can get the pointer here. If we look at the general identification, we find that they rely heavily, primarily, on the Asperities. And if you take a look at bright and actually current individuals, what they have done is to say that there will be anywhere from 4 to 6 of these. Now, some indicate that they may be broken and therefore the 6 become 12, but technically speaking, the crescent-like Asperities are the main features of identification at this particular time. Nevertheless, if you start counting, you'll find that this one has 8, and the other specimens that we looked at have 8. So there's a good chance that by looking at them a little closer under the scanning electron microscope, we may have to expand our understanding of the features that identify this particular species. We take a look at the Asperities a little closer, like a head on, and we see that it actually consists of a series of microplates. Very interesting. And these are actually raised, although we couldn't, for the life of us, see it under a stereoscope. But if you'll take a look, these are somewhat raised in a method similar to that. I'm thinking like a snake and scales, to allow it to, that's our hypothesis anyway, is that it allows it to tunnel through the tissue. And another thing about these microplates is that there's a seta associated with each one. If you'll take a look, a little microplate joined with the next microplate, but a seta. And these are barbed seta, very barbed, very common, but quite distinctive. Another characteristic that we can take a look at would be the antennae, of course. And it is a 7-segmented antennae. The club section here is actually composed of 3 final sections or segments. That would give you your typical 9-segmented antennae that you find in the common insect world. So we have that. Another factor that's involved here that is quite unusual and unique is the existence of a very rare type of seta, these branched or palmate hand-like seta that are arranged in a row around the pronotal area just above the compound eye. Above it, of course, you'll see the basic seta that you'll find on the exoskeleton, and that would be the barbed seta. And if we take a lateral view of it, we'll see that these palmate or branched seta, quite unique, run the entire length of the pronotum on the margin. And on the posterior margin, we find that it would be all these branched seta that make up the fringe there. In addition, if you take a look at the compound eye, we'll see that WTB has a notched compound eye. Here we go, right here, just almost like in a Hymenoptera with some of the wasps. In addition, it has legs that are basically the same size, so it's quite unique in its morphology. In our collections, we found that this particular insect, the walnut twig beetle, begins to emerge in mid to late March here in East Tennessee, and then subsequent generations then emerge until about the first week in December. We think that there's an overlapping generations here in that we can see at least 3 peaks. So we would conclude from that and the length of time that it takes for the insect to develop from egg to adult, that perhaps there are multiple generations here in East Tennessee of this, while it is continuous and we would perceive it as looking as though it were one generation. There is the possibility that there could be a couple of generations within that time frame. I mean, even as it only takes about 2 months for it to go from egg to adult. So once the insect, the female, has found her host, colonized the host, she immediately begins to bore into the bark, developing her tunnels to lay her eggs. And she lays these little cream-colored eggs, and these larvae that hatch from the eggs will then produce, as you well know now, undivided tunnels or galleries. Now, while we do not know yet just how many galleries each female can produce, simply because it has come to our attention that she lives a lot longer than we ever thought that she did. She lives longer than 2 months, we know that. So she can produce a multitude of galleries during her time underneath the bark. Catherine has found that by looking at the eggs from individual galleries, that there is a range of eggs that she lays ranging from 7 to 25. And as time goes on, we'll probably refine the mean for each gallery, so that it gives you some idea as to what happens whenever she does bore into the tree. We see that, the female then makes a horizontal gallery. She immediately begins to make or chew out little slots for which she'll lay an egg in. She'll cover the egg with frass, and then the insect then will develop and make her tunnels or his tunnel off of the female's horizontal tunnel. And here is a picture that Dave just obtained a few weeks ago, showing and confirming that the female makes more than one gallery under the bark. Before, we kind of suspected it, but we had no proof. But she'll make them at different matrices or different levels in the bark. So that's why we see sometimes almost no tissue left where heavy infestations exist. And then it, of course, eventually will show up, the Geosmithia will show up in the female galleries. Once we decided to determine how many eggs can this female produce, we began to look at the possibility of isolating them, because bringing 6-foot logs in became a problem because we could never tell where one female began and another female ended or something. So we began to isolate and put one female and one paired group in a container with a small boat. And then we can follow these over a period of time. Well, again, we missed our mark. We underestimated. I thought for sure, based on other biological data for other bark beetles and whatnot, 6 or 8 weeks would be sufficient. But we ran ours for 10 weeks. But it looks like we're going to have to run the test again for 20 weeks, simply because after about a week, the female begins to produce eggs. After the second week, we see larvae developing. After about the 6th through the 10th week, we see pupa developing. And after the 8th week, adults, teneral adults, occur in the tunnels. Also, the adult female was actually found 10 weeks post entrance in her making the tunnel. So she's a pretty long-lived. We just don't know how long as of yet. So it should be kind of interesting to finally put a longevity period for her. In regard to that, then, all of these multiple egg clutches then produce an overlapping population or populations, and perhaps several generations in a year's time. The life cycle is about 8 to 9 weeks. And each female we have projected produces at least 50 eggs. And we're thinking more like over 100 if she can continue to live after the 8-week period of time and produce additional eggs. Then she has a fantastically large fecundity capability. And then the fungal pathogens have been only found to this point in the pupa and adult tunnels, as well as the tunnel that the female originally made. Another question that it was asked was, how does the Conidia or how does the TCD get into the tunnel? And so we were fortunate to find the Conidia on the specimens using the SEM. And if we take a look, we see, go back. If we take a look, we can see, maybe if I can get this right. Single, attached, some clinging in a chain-like formation. In the seta, here we have some, here we have another one. We have them just adhering to the exoskeleton as well as to the barbed seta. And as she digs her way through the tunnel, makes her little slots for her eggs, she also deposits and can deposit the Conidia in those areas. So that might be an answer as to how progresses throughout the tree and how the number of galleries that the female produces might be an aid to development of the Conidia. If I might, with just the last couple of minutes, I would like to mention that we are still working on our biological control studies. We're still collecting predators that might have potential use against the WTB. To date, we've identified 13 such predators. If you'd like to know more information on that, you might like to look at Catherine's poster on the predators. We're looking at behavioral activities also for two of these particular species, Medoniella discoloides and Parasitoid Theocolax. And we're looking basically at the consumption rates for the different predators. And thus far, we're finding that 2 is quite low, and we're not quite sure just how much we can count on these predators at this point. And we're more excited about the parasitoid that's pretty common in this area. It is, although initially difficult to find, once you find it, you can continue to rear it and enlarge the colony. It's an ectoparasitoid. It feeds in the tunnel on the larvae, and we are now developing methods to determine what the fecundity level for each of these parasitoids might be, so that we can also rear the parasitoid in mass, perhaps one day in the future. And I'll leave it to that. Yeah.